coming today. The weather is beautiful out. I'm sure it kind of is a little depressing to be in this cave. I wish we could have a talk outside, but kind of limited by multimedia things here. So today I'm going to focus on multi-messenger astronomy. And as always, I encourage questions throughout. Don't hesitate to ask me any burning questions you have mid-lecture, and if things get a little out of hand, we can delay the rest until the end. All right, so by multi-messenger, I obviously mean multiple messengers for astronomy. The messenger we're all familiar with are electromagnetic waves. That's what's been driving astronomy for the most part over the last few centuries. But there are other messengers. There are other carriers of information that the universe gives us. One example are cosmic rays. Those are charged particles with a crazy amount of energy that we detect sometimes on Earth, as well as neutrinos, which are very light, fast-moving particles. Also not light, they have some mass to them, but they also carry information from great distances. And finally, our favorite, gravitational waves, are that new messenger that we finally detected for the first time. So neutrinos are something that have been detected since about the 1980s in an astronomical sense. They travel very close to the speed of light, which means that they have mass that is very, very, very tiny. Only massless particles, truly massless particles, travel at the speed of light. And so if you give it just a little bit of mass, then it has to travel a little bit slower than the speed of light. And neutrinos are an example of that. They're kind of a crazy particle. They actually exist in three different flavors, we think, three different types of neutrinos. And they're actually not in a steady state as they travel. They don't stay as one neutrino. They can actually oscillate between neutrino types as they travel, for example, from the sun to the Earth. Because they are so high energy, because they travel so fast and they have such little mass, there's a very low probability that they interact with anything on Earth. Most neutrinos pass clear through the Earth without interacting with a single thing. So detecting them is a pretty challenging task. And it requires a huge amount of volume. Our detectors have to have a huge amount of volume to them to increase that probability of an interaction by any given neutrino as it passes through. Here is an example. Super K is the nickname for it. It is a detector in Japan, deep in a mine shaft, and there's some people over there for scale. It's a huge, huge room, a huge chamber. All of these little orbs are photomultiplier tubes, and this is filled with ultra-pure water, about 50,000 tons of ultra-pure water. And the idea is that as a neutrino passes through, it has some very small probability of interacting with that water. And when it does, it creates all kinds of radiation that we can actually detect more easily. And so all of these photomultiplier tubes are watching that volume of water, looking for that triggered radiation from a neutrino interacting with the water. So this is one example. There's a few different neutrino detectors like this around the world, all operating in unison. Another type of detector is IceCube, which is something that is led out of University of Wisconsin-Madison. And here is this is the main lab area. This is at the South Pole Station. It involves deep, deep holes being drilled in the ice. And then down those deep tunnels, they drop strings of these orbs, of these DOMs they call them, digital optical modules. Each string has about 60 of these DOMs. And the whole apparatus is huge. So there is the Eiffel Tower for scale. Here is the surface of the ice at the South Pole. And that's the array of DOMs down there. And the principle is very similar to the Super K detector that I just showed. They use this huge chunk of ice as their volume, and they look for interactions of neutrinos with that volume of ice. And they take advantage of the ice at the South Pole. It happens to be very, very clear, especially at those depths. And so that's how they go about detecting neutrinos down at the South Pole. Any questions before I get on neutrinos in the back?
Do the neutrinos or any other particles that you study experience quantum entanglement from which we can infer more information?
So I think getting into those details is probably a little bit beyond the scope of this talk, but I'd love to talk with you after about that more. Okay. So come down if you want to talk about that after the lecture. Any other questions on neutrinos before I move on? All right. So the other messenger that I mentioned before gravitational waves were cosmic rays. And these are also massive particles, but they're typically protons, neutrons. They're run-of-the-mill particles. They're just traveling at insanely high energies. And they come to us from, we think, outside of the solar system. We don't think there's anything in the solar system that would produce cosmic rays. That's contrary to neutrinos. Neutrinos are produced by the sun through fusion and other things, triggering these neutrino production. But cosmic rays, we think, are only generated outside of the solar system through things like active galactic nuclei and other things that are very, very energetic events in the universe. And we detect them similar to neutrinos. We look for the triggering of radiation emitted as it interacts in the atmosphere. And so we get the shower of particles and light triggered by a cosmic ray interacting in the atmosphere. And we have instruments on the ground that detect them. So this is Veritas. This is one example of a cosmic ray detector that looks for that Cherenkov, that triggered radiation of interactions of cosmic rays with the atmosphere. Cosmic rays also affect space-based telescopes that don't look for gamma rays necessarily, or sorry, that don't look for cosmic rays necessarily. So Fermi is one example of a space-based telescope. It's a gamma ray telescope. And it has to deal with cosmic ray impacts on the CCDs all the time, and it can look like a gamma ray, and so they have to have data analysis algorithms that can separate out cosmic ray hits from gamma rays.
Isn't it true that most cosmic rays are proton, primary cosmic?
That's right.
We have no, theoretically it could be any particle, but they seem to be mostly protons. Do we know why?
So that, I don't know if we know why. I don't know why. But I don't know if people know why protons tend to be the favorite particle. But it's an interesting question. I mean, the mechanism for generating cosmic rays is still unknown. I mean, we think we have an idea of what kind of sources will emit cosmic rays, but it's still a rather shaky theoretical ground for actually predicting the generation of the full energy range of cosmic rays that we detect. All right, so gravitational waves, that final messenger that we just added to the mix. So to remind you of the source classes that we have with LIGO, the kinds of gravitational wave emitters that we can detect with LIGO, we have the continuous wave, the burst sources, the compact binary mergers, my favorite, and stochastic background. So the top three are examples of gravitational radiation produced by individual events. And that stochastic background is the superposition, is the combination of gravitational wave from multiple events, from a population of binaries, for example, will create that stochastic background. So if we're looking for multi-messenger astronomy, we're looking to tie together electromagnetic radiation, neutrino detection, cosmic ray detection with a gravitational wave event, we need an individual source to cause that common ground, to be the common source of all of those messengers. And so stochastic background is not something we're interested in. So I'll just focus on the other three. So to remind you about continuous waves, these are sinusoidal gravitational waves. It's a constant frequency picked up by the instrument over a very long duration of time. The most likely emitter of continuous waves are pulsars, or neutron stars specifically, that have some asymmetry. They have a hill on them and will create this constant frequency gravitational wave. And the multi-messenger component of that is if we can see them as pulsars, if we can see that very regular pulsation of light that's caused by this lighthouse effect. If the neutron star has a very strong magnetic field, which we think most do, it beams the emission of light from that neutron star, and that axis of the magnetic field can be misaligned with the rotational axis, and it creates that lighthouse effect. We see that all the time in the Milky Way. And so we can try to tie together the information from radio observatories that pick up these pulsars and tie that to the gravitational wave data that we collect. And so that can feed both directions. So often when we talk about multi-messenger astronomy with LIGO, we take advantage of its all-sky capability. Each instrument can detect gravitational waves from everywhere on the sky at any given time. Most telescopes have to be pointed. And so the most likely direction of information travel is that LIGO will detect something from somewhere in the sky. And then we send that information, we send our best localization that we can give to telescopes that point, and they can look across that localization region and try to find where that source was in electromagnetic radiation. So continuous waves are an example of where that may actually go in the opposite direction. We know lots of pulsars in the Milky Way, and we can use that information to look very specifically in the LIGO data for those continuous waves, for those single frequency gravitational waves. One example of where we've already done that is the Crab pulsar. So this is a nearby pulsar that we know exists, and any asymmetry would create some kind of radiation that we would pick up with LIGO. And so we do that. We call it an externally triggered search. We know exactly where on the sky the Crab pulsar is. And so we can use that to very specifically look through the data for that very specific frequency in that very particular spot in the sky. And it gives us an ability to dig much deeper into the noise than we could if we didn't know that information. Unluckily, the pulsar, the Grab pulsar, oscillates at a frequency that puts it in directly in our 60 hertz noise, which is the line generated by the power, by alternating current that goes to the detectors. So it's actually really hard to search for the Grab pulsar, but there are other pulsars that we also search for. All right, finally, burst. So burst is a kind of all-encompassing class. It doesn't apply to any particular electromagnetic phenomena, but one very likely one is a supernova explosion. So these supernovae we see go off in the universe all the time. They don't go off in the Milky Way all the time, luckily for us, but they do occasionally happen nearby, and we need that to detect them in gravitational waves. We don't expect the gravitational radiation from stellar explosions like supernovae to be that strong, so we can't see them that far away. If the supernova goes off in the Milky Way, or in the larger small Magellanic Clouds, we'll detect it. But otherwise, it's going to be very hard to detect, so we need them to be close by. And we also have the added messenger, so beyond just gravitational waves and light, we have the added benefit of neutrino messengers from supernovae. We think that they produce lots of neutrinos, and we would detect them with neutrino detectors at the same time, roughly the same time that we detect the gravitational radiation with LIGO and the electromagnetic radiation with telescopes. So one example of multi-messenger astronomy that's already happened is supernova 1987A. So this was a supernova that happened in the Large Magellanic Clouds, so right in our galactic neighborhood. And it happened, it was so bright, you could actually see the supernova with your naked eye. And the radiation, so here's the remnant of that supernova, as viewed by Hubble. And so the multi-messenger component of this was we actually did detect an excess of neutrinos. We detected more neutrinos than we do on a typical day at the time that the supernova went off. Actually, a few hours before the supernova went off, because the neutrinos are the first messenger to make it out of that explosion. Because they interact so weakly, they can be generated at the very core of the star as it's starting to explode and escape that star without any kind of impedance. It doesn't have any opacity. The star doesn't have any opacity to hold that radiation in. So we detected that a few hours before the rest of the light came. I say we, I wasn't even born yet, but the humans detected the neutrino radiation a few hours before the electromagnetic radiation. So that was the first, I would say, multi-messenger astronomical event, but we hope to add plenty more to that over the next coming years with LIGO. So I'm going to focus now on the last class that we hope for multi-messenger astronomy. Before I do, any questions on what I've talked about so far? In the back, yes?
Well, will it be possible in the future to detect gravitational waves from our own solar system, like the revolution of Mercury around the sun?
So every planet does generate gravitational waves. The strongest emitter of gravitational waves in our solar system is the Jupiter-Sun system. But that is still many, many, many orders of magnitude too weak for us to ever hope to detect. So it's very unlikely that we'll ever detect gravitational waves generated from our own solar system. And it's actually hard to imagine how that would actually happen, because the gravitational waves that we always talk about are only valid in a far field sense. They only really generate in the way that we look for them when we're really far away from the source of the objects. Because we're in the middle of the solar system, we don't actually get classical gravitational waves, these very simple traveling waves that we've been talking about. You get this weird strong field, near a field effect that that is very hard to describe. So we don't have great models for that, I don't think. But yeah. Anyway, the amplitude is going to be so tiny that I don't think we ever could detect them. But people said the same for gravitational waves from extragalactic objects too, but that wasn't true. So who knows? Maybe a few centuries from now, people get really smart and can figure out a way to detect them. But right now, it looks very unlikely. Any other questions? All right, so the last and most interesting to me, at least, form of multi-messenger astronomy is going to be on compact binaries. So those are binaries containing neutron stars and or black holes. Neutron stars, so here is a numerical simulation of a binary neutron star merger. We start these two objects off as basically steady-state independent neutron stars. As they orbit one another, they emit these gravitational waves, causes their orbit to shrink, just like the binary black holes we spend a lot of time talking about. And as they merge, that matter gets tossed around. There's all kinds of energetic things happening as those two objects merge. And you see all of this matter and all the strong magnetic fields being created. And we expect that to create all kinds of interesting electromagnetic, all kinds of interesting light that we could detect. And so the same is true even if we're not smashing together two neutron stars. A neutron star black hole system, here's a simulation of that, we think will also be a very strong emitter of electromagnetic radiation, not through the direct collision itself, but of that tidal disruption of the neutron star as it gets close to the black hole. So play that again. As the neutron star gets close to the black hole, depending on all the details of the system, the mass ratio of the two objects, for example, that neutron star gets disrupted before it actually collides with the black hole. That matter gets thrown all around, can create all kinds of interesting emission, and then it forms into the accretion disk and kind of cools down. And as it does all of this, we think that there will be lots of electromagnetic light being generated that we could hope to detect.
What does that plane represent?
So what's the plane?
The plane, what does it represent?
Oh, the plane. So that's, I think, the grid. That's just showing you the grid representation that the numerical simulation used. So these simulations are incredibly difficult to do. It's hard enough to model two black holes in a binary system orbiting one another and colliding, because you need to have a huge range of resolution in your simulation. At very near the singularity, where there's this point of infinite density, you need to have a very, very dense sampling of your grid in the numerical simulation. As you get farther out, you can't sustain that level of resolution because it's just too computationally demanding. So the grid is almost an art that these people use for these simulations. And so I think they show it here to kind of show off their grid capability. All right, so those are the compact binary aspects of these events. These are the details that matter for the gravitational wave detection. What actually happens with the light, how that radiation actually looks to us, is a different question. So gamma ray bursts are one example of a very common electromagnetic phenomena that we detect in the universe. So here's a neutron star. It's just gone through some energetic event. Either it's going through an explosion or it just merged with another neutron star. The magnetic field of that body creates this jetted emission, which we see coming out here. These are very highly energetic particles traveling almost the speed of light. Here is what is starting to impact with the interstellar medium. So it's starting to hit this low density cloud, and that causes that very ultra-relativistic, that very, very fast-moving those particles to slow down. And then if we happen to be looking down the barrel of the gamma ray burst, then we see very, very, very bright emission, first in gamma rays and then in loads of other waves. So here's a cartoon representation of the gamma ray burst. So at the very center here, we have some compact object generator of this light. At first, when that jet first forms, we see this bright burst of gamma rays. We happen to be facing down the jet. And then as all of those very, very fast, high energetic particles hit into the interstellar medium, they create this shock wave. And that shock wave causes different kinds of emission as it moves out. So very early on is when we have this what's called prompt emission. That is mostly gamma rays and X-rays. And then as that interstellar medium gets hit, it slows down those particles and they start emitting at longer and longer wavelengths. And that's what we call the afterglow. So the afterglow starts off in the X-rays, very high energy. And then as that shock wave slows down, it starts to go to longer wavelengths. So visible light, eventually radio waves. So this is something that we know exists. We know these happen in the universe. There's instruments that have been detecting gamma rays for a decade or two. And the afterglow aspect, so not the prompt emission, but the afterglow aspect is something we also know. So there's been instruments that have been launched to look specifically for gamma rays and find them fast. And then once we find them, we can point telescopes. We can point optical telescopes, we can point radio telescopes, and look for that afterglow emission, and we do see it. But we don't really know for sure what the central engine is. There's different types of gamma ray bursts. There's short gamma ray bursts and long gamma ray bursts. Long gamma ray bursts, we think maybe just a single star going through a special kind of explosion. Short gamma ray bursts, the leading theory is that they're compact object mergers, so either binary neutron star merger or a neutron star black hole merger. But we don't know for sure. The only thing we can see is this kind of radiation, and we can think of ways of generating all of that kind of radiation through multiple different mechanisms. So LIGO, we hope, will be the very first instrument capable of telling us what the central engine is of these gamma ray bursts that we've been observing for so long. But to do that is going to be very, very difficult. Because this radiation is so beamed, because the jet that forms has such a narrow opening cone, we're very unlikely to see in gamma rays a given merger as it happens, because there's just such a small area of that emission that is actually going to be pointed at us if we're lucky enough. So the ones that we do see tend to be very, very far away, far too far away for the gravitational waves to be detected if there is a compact binary central engine. So we need to be very lucky to be able to connect gamma ray bursts to binary neutron star mergers or neutron star black hole mergers with LIGO. Either we need to get lucky enough to have a gamma ray burst that is pointing at us that's also close enough to detect that radiation, or, which is more likely, we're going to have to detect what we call orphaned afterglows. So as this shock wave travels out, the opening angle of that shock wave, it starts off at the opening angle of the jet of those gamma rays, but then as it slows down, the emission becomes more and more broad, and it starts to open up until eventually it just emits a full sphere of radiation. But the wavelength that it does that at is also dependent on how fast the jet is moving. So it starts off with highly beamed emission, mostly in X-rays, and then as the shock wave slows down, it starts emitting in visible and radio in a more broad way, in a more isotropic form of emission. So those if we can detect the longer wavelength light, maybe X-ray, more likely visible or radio, if we can detect the afterglow emission without having been triggered by the gamma ray burst, that's so far the only way we've been able to detect this emission. We detect the gamma ray burst aspect of it, and then we look with the telescopes and watch for that later afterglow emission. If we can get lucky enough to not have to trigger off from the gamma ray emission and just detect that late time visible light and radio waves, then we don't need to be facing down the barrel because that emission is broader. So LIGO will have to be the trigger for that. We'll have to look for these orphaned afterglows with triggers from LIGO, from the gravitational wave emission, if it truly is a compact object central engine. Yes?
What angle is the cone?
So we don't actually know for sure. All we know is that we detect it. And the only way that we could ever estimate the opening cone, because we can't send instruments out to be outside of that cone, the only way we can actually tie together data to figure out the opening angle of that cone really is by knowing the rate that these happen. So if we know the underlying rate of how often these central engines generate gamma ray bursts, and then we take the data for how often we actually see the gamma ray burst, that gives us information on how far open that must be. But we think it's about 10 degrees. So the other way that we can try to pull that information out is actually in the details of the afterglow. So the emission of the light as it's traveling out, so that those highly energetic particles start off very close to the speed of light. When they do that, the type of radiation they create, called synchrotron radiation, is actually very beamed itself. So if you have a particle that's generating the radiation, it's moving close to the speed of light, then the emission itself that it generates is very beamed through special relativistic effects. As those particles slow down, their beaming becomes less intense. And so as this shock wave expands out, in the very beginning, we only see a very small patch of that shock wave because the emission from the outspanding shock itself is very narrow and very beamed. As time goes on, we start seeing that emission becomes less beamed. We see a bigger and bigger patch of that shock wave until we can actually see the whole shock wave once the particles have slowed down enough. So once that happens, we see a kink in the afterglow emission. And that kink gives us information on how wide that jet has to be. But all of that is very hard to do. People argue whether we've actually seen that kink in the afterglow emissions that we've observed so far. If you assume that we have, if you give people that credibility, then the estimate is about 10-degree opening angle. Any other questions? All right, so this is also something that LIGO will inform, because LIGO can detect the inclination of the binary. So it can figure out what the orbital plane looked like to our point of view, and then we can take the information on whether we saw the prompt gamma ray emission or not over a whole bunch of detections. And eventually we could hope to inform more rigorously what that opening angle is, but that's going to be a long way down the road. So that's all gamma ray bursts and afterglows of gamma ray bursts. There's another model for electromagnetic emission that's been talked about a lot lately in the literature, which are called kilonovae. They get the name because they are about a factor of 1,000 more bright than a regular supernova, so they call it kilonova. And the mechanism we think is very similar to gamma ray production. So we think that gamma ray bursts may also be at the same time generators of kilonova emission. But the problem is that kilonova emission is rather weak. It's 1,000 times the supernova emission, but it's very hard to find. So gamma ray bursts, the things that are generating these things we think, are very far away. So detecting this weaker emission is very hard. The reason it's appealing for gravitational wave multi-messenger astronomy is that emission is not beamed. It's very isotropic emission from the very start. So if we detect a gravitational wave from a binary merger, it doesn't matter the orientation of the plane. We hope to be able to detect this kilonova emission that's actually generated. The way that it happens, so here is the final remnant black hole. Was there a question? So there's been a merger, either a binary neutron star or a neutron star black hole merger. We get this black hole left at the end. We have some matter around it from the tidal disruption that happened and the leftover matter from the merger process. All of that matter is in a state that creates this rapid neutron capture. It creates what's called R-process nucleosynthesis. That creates very, very heavy, unstable elements that quickly decay and generate this overall emission that goes in all directions, we think. And so here's an illustration of the R process as it happens. So on the x-axis here are the number of objects in the nucleus of the atoms being formed, and on the y-axis are the number of protons. And this is only a few seconds long. You see this shot through to very, very heavy elements very quickly, within a matter of a second or two. All of those very, very heavy elements are unstable, and they quickly decay and generate this type of emission that we're looking for. So this is something that's been theorized. We think we've detected it. We look for it after gamma ray bursts. Because it's so weak, most gamma ray bursts that we detect, which are very far away, we are very unlikely to find it. So there's been one possible detection of kilonova emission so far. And this is a Hubble image looking for that emission afterward. But the details are very complicated. Because we've never detected this, or maybe we've detected one, we're really forced to rely on theory. And the theory that goes behind generating what we expect that kilonova to look like, and therefore how we expect this emission to actually happen, what wavelengths to happen, is very uncertain. So it depends on exactly how the R process nucleosynthesis progresses, how quickly all of that happens, and then the type of matter that's left over after that merger. So particularly the opacity is very uncertain. So the very first models that came out for kilonova emission they predicted radiation that was going to be very blue. So basically blue type emission in the visible spectrum, and very quickly dying off. So over the course of a day or two, fading. But then there were updates that came. So now the leading model is that the opacities are higher than the original predictions had claimed. And so that creates more red emission, but it also creates a longer time scale for that emission. So then that would actually last over like a week or two. And that's more appealing to us. So the latency with which we can give localization with LIGO is really dependent on the type of source. We hope to be able to get out localization information within less than a day for sure. But then we give these huge areas in the sky. And most telescopes have a very narrow field of view and have a very hard time following up that gigantic patch of sky that we say the source was in. And so we need time to be able to find that emission. If we have emissions that happen in a week or two, that gives astronomers a lot of time to search the big areas that we produce with LIGO and try to find that emission. The downside is that there's lots of things that happen in big patches of sky, and so then tying together electromagnetic information with gravitational waves and knowing that those have the same source is very difficult.
Is that the same as a hypernova?
My guess is no. I'm not actually sure what the hypernova is referring to.
Just a lot bigger.
Yeah, so no, I don't think it's what would be called a hypernova. All right, so here are the time scales that we've been talking about. So this is a time scale in seconds. So we have about 1 second down here, and days to weeks to months over here. And on the top are these different electromagnetic activities that I've been talking about so far. So we have GRBs here at very short time scales, the X-ray and optical afterglows from those gamma ray bursts, kilonova emission, and then the radio afterglow from the gamma ray production, from the gamma ray bursts. On the bottom here are the latencies, how quickly we can give information from LIGO. So we detect things on the order of minutes to an hour after they are actually incident on the detectors, after the radiation hits the detectors. We can localize them very soon after, crudely, get this kind of information here. So this is a low latency localization of a simulated signal. And then on the order of days to maybe a week, we can give really fine-tuned localization. And so this is an example. If you wait a week, how well we can localize sources on the sky. So the star, in this case, shows you where that simulated source was on the sky. This red region shows you the sky map that we would hand off to electromagnetic partners to point their telescopes at. And so The details of how that map evolves over this time scale here really depend on the state of the network at the time. So the network, our localization ability comes from time of arrival differences at first order. So the delay, so that as the gravitational wave from a given source passes through the Earth, it's going to hit the detectors at different times. The delay times we can use to triangulate where on the sky that source came from. If we only have 2 detectors, the best we can really hope to do with just timing alone is a big ring on the sky. If we have a 3rd detector, then we can start, even if it doesn't detect anything, we can use that information to restrict where on the sky that came from. So this is an example of a 3-detector detection. So this is the 2 LIGO instruments and Virgo. The detection, actually, the signal was loud enough to detect in the 2 LIGO instruments, and Virgo, it was below the noise level in Virgo, so there was no detection, no clear detection in Virgo. This full parameter estimation that I talked about last week is able to completely take into account all of that information. And not everywhere on that ring would produce no data in Virgo, would produce no detection. Some parts of that ring, if there were actually a source there, would have created detectable radiation in Virgo. And that information is taken into account. But it takes about a week to do that. Question?
So if I understand you right, there's been a lot of detections from LIGO other than the 2 black holes that have emerged. How many detections or possible detections have there been?
So the only detections that we've published on are the one famous detection, the GW150914. There's a second object that's talked about in that paper, a second event. It wasn't above threshold, so we don't call it a gold-plated detection like the main one. But it is very likely a gravitational wave. We just can't say it with very much certainty. So right now there's only 2. This is a simulation of a signal. So because we've been operating for decades, but we've only just now detected gravitational waves, we got really good at simulating them to figure out what we could do with these instruments. So this is an example of a simulation. So right now there's only been 1 clear gravitational wave detection that's been discussed. But we have more data in the can. So only the first 16 days of the observing one were published. So we have another couple months of data that we haven't published on yet. And then we will be taking new data at the end of the summer. The second observing run starts off in the end of the summer, and that will go for about 6 months. But right now, the only detections are this GW150914. Any other questions? Yes, in the back.
Why, is there some reason why you cannot collect data continuously?
Yeah, so keeping the lasers in lock is actually very tough. So the way the whole LIGO system operates is it's all one big active control loop that keeps the mirrors stationary to keep the whole laser system in lock, to make sure all the radiation is in phase like it should be. Seismic activity, earthquakes in New Zealand can knock the LIGO detectors in the US out of lock. And we have to wait for the ground to settle down enough to be able to get the instruments back into lock. So things like that happen all the time. Various components need to have some maintenance done to them. So there's lots of various things that can cause us to lose lock in a laser or to have to take it out of lock for some stretch of time. We try to minimize that as much as possible during the observing runs. And so we strive for as much coincident data as we can, where we have at least 2 detectors operating. If we only have 1, it's kind of useless because we would never claim a detection of gravitational waves with 1 instrument online. But we try to minimize that. But it's a huge range of issues, from seismic noise to instrument maintenance, that take us out of commission for some stretch of time. All right. Any other questions? All right. So far we've talked about binary neutron star mergers and neutron star black hole mergers as producers, we think, of electromagnetic radiation that we could use to do this multi-messenger astronomy that we hope to do. The one type of compact binary that I haven't talked about yet is, in some ways, the most interesting one. It's the one we've actually detected so far. Binary black hole mergers. Here's that favorite simulation of GW150914. We had a 29 solar mass black hole falling into a 36 solar mass black hole. Here we're showing the star field in the background, and the black holes, the actual black component here is the event horizon of each black hole. And the only effects that we're seeing are the lensing, the gravitational distortions that change the path of light from that background star field to us. So if we were actually looking, if we happened to be lucky enough to be pointing a telescope at exactly where this event happened, when it merged, we wouldn't have detected anything. These little changes in the path of the light from the star field behind the object were way too tiny to ever hope to detect with electromagnetic telescopes. So the question is, what kind of electromagnetic counterparts do we expect from a binary black hole merger? And the answer is we have no idea. So we don't expect anything. We expect that, but these binary black hole systems have existed for so long that any matter that may have been left over from the black holes forming has been either taken up by the black hole or been ejected out of the binary system. So we really don't think there's going to be matter around. We can start to come up with some exotic ways to have matter around to create electromagnetic radiation that we could detect. One way, so that I don't know. So that there's a kind of age-long feud between theorists and observers in astronomy, and theorists that are always joked that they can come up with an explanation for anything. So we have our gravitational wave detection, GW150914. There was a whole bunch of electromagnetic follow-up. There's some hints that there might have been some electromagnetic counterpart. And I think it was like a day it took for there to be a theory paper on how you could expect electromagnetic radiation from a binary black hole merger. That mechanism, I think, I don't even remember all of the details, but it was something about binary black holes forming, so you have a binary system forming within a big star, and basically that merger triggers some kind of explosion that can produce emission. But anyways, so you can bend things, you can come up with a whole bunch of unlikely things that lead to electromagnetic emission from a binary black hole merger, but we really don't think that there's going to be electromagnetic radiation from a binary black hole merger. That doesn't mean we shouldn't look. We find things that we didn't expect all the time, so we are doing our best efforts to give the proper information to astronomers to then follow up binary black hole mergers that we detect with LIGO and to look for sources. This is the localization region we had for GW150914. So we only had 2 instruments online, but this isn't a ring on the sky. We actually did a lot better at localizing the source than just a ring on the sky. And that comes from the extra information that we can get out of the data besides just time of arrival. So from the time of arrival alone, we get a ring on the sky. But because those antenna patterns, so we're not exactly omnidirectional instruments. We are more sensitive to gravitational waves that are coming at the detectors from above and below, rather than on the sides. So the shape of the antenna pattern, if you were to draw a shape that shows our sensitivity around the detector, it's kind of peanut-shaped. And so the detectors of LIGO are not exactly aligned. One is in Washington State, the other one's in Louisiana. So there's a slight misalignment of those antenna patterns. And that provides us a little bit of extra information on where that source could have been on the sky. If it's in a part of the sky where it hits those peanuts at a slightly different part for each of the detectors, then that causes a change in the relative amplitudes measured at the 2 instruments. And that gives us a little bit of extra information on where it was in the sky. So all of that information, taking into account that full parameter estimation sky map that I showed you before, this is where we localized the GW1509 source loop. The areas, so this is what we produce as a probability map. And these contours are enclosing a certain amount of probability. So that inner contour shows you where 50% of the probability is for that sky map. And this outer contour is 90% of the probability. So it's 90%, you have a 90%, if you search this whole area that we highlighted here, you have a 90% chance of having the source be found, or at least you pointed at the source, whether or not it emitted any electromagnetic radiation. So those are our sky maps. The areas, the 50% area is about 140 square degrees, and the 90% area is about 590 square degrees. This summarizes the campaign conducted by our electromagnetic partners to search for a possible electromagnetic counterpart for GW150914. So on the very top here is showing so this is the horizontal direction here is showing the time in days after the detection. And the different colors represent different bands in the electromagnetic spectrum. So in blue here is showing the X-ray and gamma ray searches. In green shows the optical. And then in red shows the radio wave searches. So there's a whole lot of resources that went into following up GW150914. Even though we didn't have a strong theoretical underpinning for there being electromagnetic radiation, that doesn't mean we shouldn't look. Everybody's really excited for multi-messenger astronomy and for finding things that we didn't expect. That's sometimes the most interesting. You had a question?
Yeah, on that previous screen, what was that little blip of 90% on the top?
That little blip. So that just gets into the nitty-gritty details of exactly how the gravitational radiation projects onto the 2 instruments. So this area right here is very unlikely for various reasons. Either it's it would need an unlikely orientation of the binary to create radiation that's consistent with what we detected in the 2 LIGO instruments, or there's some polarization content mismatch with the orientation. So The details are complicated, but it's basically just saying that this is a very unlikely part of the sky. But then there's a little patch up here where you could actually get a reasonably likely signal. You're likely to produce something that like what we detect in the instruments. So the answer is not clear. It really gets into the very details of that whole machinery that I talked about last week, where we have this probability density function is actually a 15-dimensional function. And the models are very complicated for how we can generate the actual gravitational radiation we expect to measure at the instruments. So there's a whole lot of knobs to turn. And once you turn all those knobs, this is the answer that we get out. But the understanding at a very fundamental level, all of the aspects takes a long time to really get into all the details. Yes?
I'm not clear what you were trying to show with that next graphic, where you had all the optical or electromagnetic activity that was looked at, and how it relates to or doesn't relate to. I mean, did you find anything or not?
I'll get to it. Yeah. All right, so that's just giving you the time scale for each band of how searches were done for this. So remember the gamma ray burst model, the afterglow model that I talked about before. You had prompt emission in gamma rays and X-rays. You had early afterglow emission in X-rays, and then at longer timescales, on the days to weeks, you get the visible light to radio waves. So that's a general kind of characteristic of these transient astronomical events. You expect the short wavelength stuff to be short duration, and the long wavelength stuff from a single source to be long duration. So you can see that there's some searches done in the high energy band early on, and then the lower frequency stuff, they weren't that quick to act on it. The radio waves, they took a while to observe because they don't need to rush to find the radio emission. So this is showing you that same sky map that we sent to astronomers and overlaid all of the observations that were done in all of the various bands. So again, the coloring here is the red is the radio, green is the optical and infrared, and blue is the X-ray. And there's all different kinds of patches that are on here. Each of them is dependent on the instrument that did the observing. Some have square fields of view, some have octagonal fields of view, some have narrow fields of view, some have broad fields of view. So all of these details make it really hard for any given instrument to follow up our sky maps. This is a weird shape in the sky, and it's big. And when you have a telescope that has this tiny little square field of view, it takes a whole lot of pointings to cover any significant amount of probability in those sky maps that we produce. So you have a lot of these squares in the infrared of people looking at various parts of this, trying to look at what they thought was most likely. We have these individual red circles here that are the radio. Then we have this big red circle here, which is a very wide field of view radio instrument that covered, I think they took 2 observations. But you'll also notice up here, so this dark line is the sky map from the full parameter estimation. But then there was a lot of follow-up actually out of that blob in the sky that we said was a likely direction for the source. The localization ability, so those pointings were based on the low latency information that we provided early on after the detection. And those are actually from analyses that don't even assume a compact binary caused it. So those are the burst searches that happened. And because they don't have a strong model for the gravitational wave emission, their localization is poor. And so there was a combination of things that led to those maps being the first ones sent out. The first was that we didn't have a strong reason to believe electromagnetic radiation would be produced by a binary black hole merger. So we had to set priorities with getting the first observing run going. And we weren't even in the first observing run yet. We didn't actually officially start 01 yet. And so we didn't have our binary black hole online searches going yet. And so we only had the binary neutron star searches operating and the unmodeled, those burst searches operating. And so the source was too high mass for the binary neutron star searches to find it. And that only left the burst searches to find it at a low latency, to find it very early on after the gravitational wave hit the instruments. And so the first maps that went out had to be those burst searches, which are worse at localizing compact binaries. And so it was only after a few days that we were able to run the binary black hole searches on them and then get out updated sky maps to our partners. So eventually those sky maps went out, and that triggered more observation. And that kind of explains partly the weird timing of all the observations here. We were caught by surprise. This happened way earlier and way more loud than we thought would happen. So just to highlight one of those observation campaigns, it's a local one. Dark Energy Camera is part of the Dark Energy Survey, which is run largely out of the University of Chicago and Fermilab. And they played a huge part. I think they probably covered the most area of any optical telescope, and they covered a large part of that sky area. And what's interesting, this is showing you the kind of stellar background imprinted on top of the sky maps that LIGO produces. This blob right here is the Large Magellanic Cloud. And just by chance, so there was no way that the gravitational wave emission came from the Large Magellanic Cloud. It was a binary black hole merger that was 1 billion light years away. But it just happened to overlay with the Large Magellanic Cloud. So when you combine that with the early state of things, where we only had a burst detection and no compact binary detection, it looked like it could have been a burst signal in the Large Magellanic Cloud. So you'll notice there was a concentration of observations in the Large Magellanic Cloud. That turns out to be very difficult. So the way these transient searches in electromagnetic astronomy work is you want to find things that are new. You're looking for new bursts of radiation, electromagnetic radiation, that weren't there before. And they do it through a technique called difference imaging. So you have some template of the sky that you collected sometime before. You take a new image of the sky, and you take those two images and subtract them. And anything new is going to be big and bright in that subtraction. And anything that's been there since the template image that you took a while back is going to just disappear from the subtraction. Doing image subtraction for a dense stellar cloud like the Large Magellanic Cloud is really tough, and so they're really upset that we did this. But they got it done. They did a great job with the analysis and got some useful information out of it. So to answer your question, we have to go to gamma rays. So gamma ray instruments on the handout that I gave you today have to be in space because the atmosphere is opaque to gamma ray radiation, which is a good thing for us because it would be very damaging. So we need to go to space to detect gamma rays. Fermi is a particular space-based instrument that is looking for gamma rays. And the way that they do that is actually fairly omnidirectional. They have all of these detectors throughout the satellite that can detect gamma rays coming from lots of different directions. So Fermi is one of the main detectors of short gamma ray bursts right now. And the way they do that is just through this monitoring of all those individual instruments. Because they are omnidirectional in this type of gamma ray emission, they're an all-sky detector too. We don't need to trigger them to search very quickly and to point their telescope. The LAT, the Large Area Telescope on there, is able to pick up things all around. So they're already recording the data. We just look for coincidences after. We don't need to rush. And what they did look at the time of GW150914. This is a kind of combination of the gamma ray detectors on the instrument, all of their data. And you see a spike at this time 0, which corresponds to when GW150914 hit the LIGO detectors. So that spike looks pretty interesting. They argue that this is a gamma ray burst. They think it's not an instrument artifact. So looking at the sky maps here, this is the LIGO sky map in a different projection that they used in their paper. They have, because they're very similar in LIGO, they have very poor localization ability. They just know that something triggered a whole bunch of their detectors on the satellite. And so this is their localization, which is great to see. We're not the worst. So they have no idea where it came from either, but we also have no idea, but we have some idea. So we can combine some idea with less idea and get a new probability map. And this is the combined localization. If you assume that there was a source of gravitational waves that also produced these gamma rays that Fermi detected, you can update the localization and you get this narrower sky area, mostly driven by LIGO, but some information provided by Fermi. And then you can take into account more information that the Earth was there. So Fermi is part of this sky map was actually occulted by the Earth. So the Earth actually blocked out some parts of the sky on the sky map. So if you assume that it wasn't a terrestrial gamma ray, then that blocks out some part of the sky area and you get this updated sky map. So their claim is that there was a significant access of gamma rays at the same time as GW150914, that the area on the sky was consistent with the localization produced by LIGO. If you look at their map, it's not a very, lots of parts of the sky were consistent with their localization. So that's not all that unlikely, but they claim that it was significant. I find it a little bit troubling that the Earth is part of that sky map. So there are terrestrial sources of gamma ray bursts. So lightning strikes, for example, can create bright gamma rays that Fermi can detect. They claim that the time scale for that detection is inconsistent with Earth-based sources, but it's just it's very hard to believe. It's a very low signal, and it's just we have such we think it's so unlikely that electromagnetic and gamma rays would be produced in a binary black hole merger that everybody is very, very skeptical of these results so far. And to add to that, Fermi's not the only gamma ray observatory in the sky. There's also an instrument called Integral, and they were operating at the time, and they should have been sensitive to a gamma ray burst if it were to happen, and they didn't detect anything. So that adds extra scrutiny to the claims of the Fermi team. They can get out of the argument by saying that Integral is sensitive to a slightly different energy spectrum of gamma rays, and so there's ways that they can get out of it, but it just makes it all very, very hard to believe. So we don't really know. We won't be able to say definitively whether binary black hole mergers actually produce gamma ray emission until we have lots more. And then we should be detecting gamma ray counterparts with some of these binary black hole mergers that we detect in the future. So time will tell, but right now it's a bit messy. So I think so if you ask me, there has been no electromagnetic counterparts detected for GW150914. But time will tell on whether I'm wrong and whether the Fermi team is right. And so stay tuned. With that, I'll take any last questions you have. Thank you. Yes?
So do we have any reasonable mapping of the existing black holes out there? I know we know there are many of them, but do we actually know where they are and what the relationship is to one another as far as orbit?
No, so we don't. So black holes come in two main flavors: stellar mass black holes and supermassive black holes.
Right.
Supermassive black holes we think are at the centers of most galaxies, so we know where those are. The stellar mass black holes are tough to see. I mean, we can't see the hole themselves. We can only see matter around them that emits electromagnetic radiation. So we've detected black holes in high mass X-ray binaries, where you have mass you have a black hole in a binary system with some stellar companion. It sheds mass onto the black hole, and as it falls into the black hole, it forms an accretion disk that glows like a filament of a light bulb, so hot it emits in the X-rays, and so that's why we call it an X-ray binary. So we've seen the black holes that exist in X-ray binaries that we're able to detect in the local neighborhood, but we have no idea about black holes that don't exist in those kinds of systems. So
I just wonder, because they're so powerful, they may control the orbits of other black holes, and I think of them like macrophages, out in the universe, they're just gobbling up all around.
So especially in dense stellar environments, things get complicated. So things like globular clusters, we think have a central core composed mainly of black holes. And it's a very crazy, chaotic, dynamic environment at the center of these globular clusters. So there we think binary black hole mergers may happen very often. We don't actually know. So LIGO, one of the main science goals of LIGO is to shed some light on that, or shed some gravitational waves on that, is to find these systems to be able to try to tell from their properties what kind of environments they were formed in. If they're formed in dense stellar clusters or more in the field, like the just independent stellar evolution as opposed to globular cluster dense dynamical evolution.
And the last thing, you just mentioned it. In the middle of most galaxies are supermassive black holes. So this is a chicken or egg kind of thing. Let's say a black hole can go supernova. I know it's not explained that way, but it blows up.
Okay.
Let's say it belches. It belches out a galaxy, and it stays in the middle rather than the galaxy forming the black hole. It creates the galaxy. Has anyone worked on anything like that?
So there is no theoretical underpinning for belching black holes that I'm aware of.
Right.
But,
But they're in the
so
middle.
how supermassive black holes are formed is still part of theory. So we don't really know. Either they could be formed from some crazy, chaotic, supermassive star that happened in the early universe,
Right.
or they could have happened through hierarchical mergers, where we start off with stellar mass black holes that we know we can form, and you just keep throwing them together in dense stellar environments until you get a few million of them together.
Throwing it up there.
So we have no idea.
Right.
But that's an active area of research, so we'll see.
Thank you.
Yes?
It doesn't pertain exactly to what we're doing, but you know a lot about a lot. So I'm interested in the island of stability in chemistry. Which may occur, they think, element 121 or higher, where they're no longer very short-lived super heavy elements, but they could be very long. Well, first of all, is there a limit, since all heavy elements like that are made by explosions in outer space of big stars and so on, is there anybody work the mathematics out to how heavy could we go given the most powerful explosion, so to speak?
So there are definitely people that have worked on that.
Really?
I mean, yeah, people, so that our process, nucleosynthesis, is one way that we create, we think that have these elements that exist in the universe. I mean, we can look at the things we find on Earth, and that gives us an idea of what these kinds of extreme environments can form. But because the heaviest ones are unstable, then we don't really know how far it goes because they quickly decay as soon as they're produced. So we can look at the emission from these gamma ray bursts and other things and try to look for imprints of very heavy elements being formed and decaying. But the details I don't know, so chemistry was my worst class, I'm sorry.
Do you have a thought of, could there be, you know, ion stability out there somewhere?
You mean if you go heavy enough to where it gets stable again?
Yeah.
I think it's unlikely just from the details of how the strong force behaves and what holds together atomic nuclei, because you tend to have equal fractions of protons and neutrons. As you get bigger and bigger, you start spreading out that charge more and more. And so I think that's what creates the instability for those really heavy elements. So it's not very hard to knock off protons once you get too big. So I would have a hard time imagining you can get big enough and then for some reason some new mechanism kicks in to keep it stable again.
Well, I'm thinking as the energy shells, the electron shells, get bigger and bigger and bigger, finally you complete whatever the magic number, and then it shrinks and becomes stable. It's very big, it shrinks and now it's stable.
I have no idea. It's a good question.
Little thought experiment.
Yeah.
Thanks.
Yeah, absolutely. All right, take one more question, if there is one. Got through them. All right, it's 2 weeks in a row. All right, thank you.